Might just barely make it here. All right, what am I forgetting? I feel like I'm forgetting something. Can you all hear me at home and see my screen?
Yes.
Okay, good. All right, it's 1 o'clock, just barely made it here. Let's start off just first talking about Wednesday's class. Of course, Thursday's Thanksgiving, so I technically cannot cancel class. So I will still be here. I will come on campus. I will do a lecture. And if you can't make it because you got to travel or something, you know, whatever, that's fine with me. I'm going to record the class. You'll just be responsible for what you miss. So if I give any assignments or anything like that, you just need to make sure you do those. All right. Any questions about that? Any questions about the homework from last time? We were solving systems of equations, and I asked you to take a look at the odd problems. Where are they? Uh-oh, where'd they go? Did I accidentally delete them? No, here we go. There they are. All right, so were there any questions on this? No. So you all felt okay with the systems of 2 equations and 2 unknowns? Okay. All right. Was there something at home? Thought I heard someone say something. No. All right. So today is going to be about systems of 3 equations and 3 unknowns and how we go about doing those. And then after that, we'll be done with the systems, like how to do them. On Wednesday, it's going to be all applications. So it'll be word problems that involve systems of equations. Might be systems of 2 equations, 2 unknowns, or it could be 3 equations, 3 unknowns. In this class, we do not go past 3 equations, 3 unknowns, but the methods that we're using here could be extended into higher order systems. And so then we'll do word problems. And then next week, we're going to get into a little bit of matrices and sequences. So that's the plan. And then I think we're done, right? That'll be the end of the semester, at least in terms of lectures. We'll have, today's the 22nd. So we'll have this Wednesday, next Monday, next Wednesday. And then we don't have class that following Monday because it's finals week. And then we'll have our final on Wednesday. And notice the time of our final. It's from 12:30 to 3:15. So I know our class normally starts at 1, but the way they stagger finals for the finals week, we're supposed to be here at 12:30, and that will be in class. So everyone needs to be here for that test. All right, let's get to it. So I thought I would start with something to kind of motivate the idea. So, you know, somewhere where we could see, I'm not going to do a word problem. It's kind of a word problem, but it's something that I think we can see geometrically where we would ever have a use for solving a system of equations, 3 equations and 3 unknowns. So we talked very early in the semester about quadratic functions, right? When we talked about quadratics, we said that when we graph them, we get parabolas, right? And I also said that one of the reasons we like to study quadratic functions and parabolas is because if you throw an object through the air on Earth, it's going to travel in a parabolic path. And we know that, okay? So there is always going to be some function, some parabola, ax squared plus bx plus c, that will describe the path of an object through the air. So if I throw, let's say I throw a ball, let's say I'm standing here and I throw a ball through the air, then that ball is going to travel in a parabola and then it will land, right? And there is some function that dictates exactly, tells you exactly where that ball is going to be at every point in time. The question would be, can we easily come up with the parabola? Can we come up with this function? How much information do we actually need to know about this object to recover the parabola? You understand my question? Like, how much information do we actually need to come up with the function? So we've actually talked about this before. If I were to say that I have that I want to draw a line, how much information do I need to draw a line? What's the minimum amount of information? I need 2 points, right? 2 distinct points. So if you give me 2 distinct points, there is only one line. There's only one that goes through those. So to draw a line, you need 2 points. What about for a parabola? How many points do you think you need to draw, to know exactly the parabola we're talking about? 2 points wouldn't be enough, right? Do you all agree 2 wouldn't be enough? Let me give you an example. If I put these 2 points here, and I say, draw me a parabola through those, you can do this in so many different ways, right? I mean, there's so many different parabolas that you could draw. Oh, that's not good. Let me do it this way. There's an infinite number of parabolas that go through those 2 points. So what do you think? Do you think 3 points is enough, or do you think you need more than 3? What do y'all think?
I think 3 points is enough.
Okay, so you're saying if one of those points was the vertex, then 2 would be enough, or 3? Okay, so 3 points and one of them is a vertex. Okay, I heard someone at home.
That was what I was thinking too.
Is a vertex. So if I give you the vertex and I give you 2 other points, that should be enough. Yep. Do we all kind of agree with that idea? Let's just think of it visually. If I give you a vertex, so I tell you, hey, everyone, that's the vertex. That's either the highest or the lowest point, right? Then if I give you 2 other points, I don't know, here, and let's say, I don't know, I'd have to give you 2 other points, right? Then I think maybe that would be enough. How about just the vertex at 1 point? Yeah, because of the symmetry, right? If I just give you that point, that vertex and that point, that should do it. Because you have to have symmetry. You know, on the other side of this, right? We have this this vertical line that goes through here. We would know we have to have a point on this side, right, for the symmetry. And so there would be only one parabola. Okay, so we could debate this a little bit, but what if I tell you, I mean, what is the minimum number of points you need to draw a parabola, to have the exact parabola, but none of them are the vertex? So how many points do I have to provide you to be able to come up with the equation of a parabola if none of the points I give you are a vertex? So here's a parabola. How many points do you need in order to come up with this function? Right? That's the question. All right. And we will answer this. Okay. Not yet, though. All right. Not yet. I just wanted to get you to think about what it is that maybe we can do with this. Do y'all want to know? I can tell you right now. Do you want to wait? Okay. 3 points. That's all we need. 3 points. All you need is 2 points to draw a line. All you need is 3 points to draw a parabola. So, but we need to kind of understand why that is the case. I will explain that in more detail later. But to actually do it, we're going to need to be able to solve a system of equations. 3 equations, 3 unknowns. So let's get to that. And then at the end of today, what we'll do is I'm going to give you 3 points, and I'm going to ask you to find the parabola through those 3 points. All right, so here's the homework problems for today's lesson. And again, let's just go and do the odds here, see how it goes. You can save the evens for when you're getting ready for the final if you want to practice more, okay? All right, so I wanted to remind you, last class I talked to you about that, the kid Gauss, right? Remember I told you about how he added up the numbers 1 + 2 + 3, and that he was the one who came up with this method of what we call elimination. It's called Gaussian elimination. And what Gauss was able to prove is that anytime you're trying to solve a system of equations, you're allowed to do these three things. At any point in time when you're looking at a system of equations, you can interchange any two equations of the system. You can interchange them. You can move them around. You can multiply or divide both sides of an equation by any non-zero number. We did that. We were multiplying through by a number to make like the x's go away or the y's go away. This is just saying that that's allowed. And then the last one is something that we didn't really emphasize, or I didn't emphasize, but we're really going to emphasize here today is, and this is a weird one, you can replace any equation in the system by the sum or difference of that equation and any non-zero multiple of any other equation in the system. Okay, what? It's basically saying that if you have, let's say you have two of the equations, right? You are allowed to add those together or subtract them from one another, and whatever answer you get, you can replace either one of those two with that answer. So again, this is a method. It's been proven that these three things are allowed. I'm not here to prove this to you. Why does it work? I'm just telling you this is the tool we're going to use. So with that in mind, I'm going to go after. Oh, we want to visually understand what's happening. I kind of alluded to this last time. When we were talking about a system of two equations and two unknowns, right? I said that was basically us looking at lines and trying to figure out where they intersect each other. We said, oh, they could intersect each other at one point. They could be parallel lines where they never hit each other. We'd have no solution. Or they could be the same line where we have an infinite number of solutions. And those were the three cases. When you look at when we look at systems of three equations containing three, I keep on saying unknowns. When I say unknowns, I mean variables. Okay, so what happens when we're looking at three equations containing three variables? Well, the graph of each of the equations in a system is a plane in space, a flat sheet of paper. And so if we want to know where three planes hit each other, we have all these different possibilities here. We could have, like this one shows three different planes, a blue one, kind of orange and purple. They could all hit each other at a single point, which would give us a consistent system with one solution. They could hit like this, where they all intersect each other on a line, in which case we would again have a consistent system because we have answers. That's what consistent means. But there would be an infinite number of solutions. It would be every point on this line. Or you could have all three planes stacked on one, and they're the same plane, just right on top of one another. And that's the analogy there for the two equations is when we had the two lines that were the same line. That's like three planes being the same planes, all being the same plane. That would be a consistent system with an infinite number of solutions. And then we can have inconsistent. You could have three planes that are parallel, like this, that never hit each other. Or you could have this kind of weird shape, almost looks like a tent, okay? The blue plane, the orange plane, the purple plane. There are places where the blue hits the purple. There's places where the blue hits the orange. There's places where the orange hits the purple, but there's no points that live on all three planes at the same time. So that would be an inconsistent system and have no solution. So this says that there's only really three possibilities when you solve a system of equations, and that is you're going to have exactly one answer, you're going to have no answers, or you're going to have infinitely many answers. Those are the three different things. So let's take a look at our first system of equations. Here it is. Notice we have three equations, 1, 2, 3. So we could, if you wanted to, you could label these. This is equation 1, equation 2, equation 3, just so we can reference them. And also notice the way they're written. The way they're written, all the x's are written first, then the y's, then the z's, then the equals, then a number. Sometimes your system is not given to you in that form, so you have to move things around. The important thing is that you get all three variables on the left side and that you line them up with one another. All right, so the question now is there an X, a Y, and a Z that you can plug into each one of those equations and it be true in each equation? So how do we go about doing this? Well, if we had a method for last time, we had substitution and elimination. And I told you that I like elimination because it extends to this very nicely, where substitution does not work here. Well, it's extremely complicated to try and use substitution here. So elimination is better. So here's how we're going to do it. Remember, if we have two equations and two unknowns, we know how to do it from last class, right? Two equations and two unknowns. So the first thing I'm going to do is I'm going to try and get this down to two equations and two unknowns. So I'm going to start here with this first equation and the second equation. And what I'm going to do is I'm going to eliminate the X. All right, I'm going to eliminate the X. So over here on the side, I'm going to take those two equations. All right, and I'm going to try and eliminate X. So that means I have to multiply the top equation by -3. That way, when I add these together, I will get the X's to cancel. So I distribute that -3 through, it's going to go to everything. And that gives me a new equation here, -3x minus 3y minus 3z equals -18. And then the bottom equation is 3x minus 2y plus 4z equals 9. So notice I'm doing this all on the side, right? This is kind of like separate work I'm doing over here. I've taken the first equation, I've multiplied it by -3, and now what I'm going to do is add these two equations together. So when I add down, the X terms go away. I get -5y plus z equals -9. Got it? Now, according to the method, which I put here a second ago, I can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation. Okay, so I'm about to use that. What I'm going to do is I'm going to replace the second equation. I'm going to replace the second one with what we got here. So the second equation, right? We took the first and second, we multiplied the first one, right, by -3, and then we added these together. So I can replace either one of these. It's my choice. I can replace equation 1 or 2 with this answer. I'm going to choose to replace 2. So that's my kind of first big step there. I leave the first equation alone. And now I'm replacing the second equation with my answer over there. -5y plus z equals -9. Okay. Now I still have down here the third equation, x minus y minus z equals 0. So now what I'm going to do is the same exact process, but with the first and the third. I'm going to try and make the x's go away on those two. So over here on the side, I'm done with that piece. I'm going to take the first equation, x plus y plus z equals 6. And the bottom equation, the third one, x minus y minus z equals 0. And what should I multiply by to make the x's go away? -1, right? And I can multiply either one of these. It doesn't matter which one I do. So I'm just going to do the first, well, actually, technically, it's the first equation. I'm going to multiply that by -1. It's got to go through to all of those. And that will give me a new little system over here that looks like this. -x minus y minus z equals -6. And then the bottom equation didn't change. And now I add those down again. So add straight down. Let's see here. we should get the x's go away, -2y, -2z equals -6. Now I go back to this system here. I'm going to rewrite it, but I'm going to replace the third equation with that answer. So I'm going to leave my first one alone. The second equation we got from that prior step, -5y plus z equals -9. And now the last equation, the third one, gets replaced with the answer we just got, -2y minus 2z equals -6. Are we all right? No questions?
Yes, I have a question.
Yes.
Could I replace the top one with the sum, or no? It has to
Yes.
be.
You could have replaced this one with this answer, but you have to have left that one alone. The bottom one would have to have stayed this one.
Okay, thank you.
Okay, it's your choice. Your choice. You can replace the top one or the bottom one with that answer, but you can't replace the middle one because that middle one didn't come from. Well, I should say this answer has nothing to do with the middle one, right?
Yes.
Okay, so now do y'all see now that we actually have here, and here? If we just look at those two, that's a system of two equations and two unknowns. Right? That's what we did last class. So now we have to go solve that system. These problems are long. They're tedious. Tedious is the right word. They're tedious. All right, so here we go. I'm going to go to the next page. All right, so now I'm going to be working over here on the side with this new system and just two equations and two unknowns. Now, from what you did on your homework, because you said you didn't have any issues, no one asked any questions. Can somebody tell me how they would go about solving that? What would be your approach? Multiply the top equation by 2. What variable are you going to eliminate by doing that? Z, right? So you've looked at this and you've analyzed, hey, look, it looks like it'd be easy to get rid of the z's if we multiply by 2 here and pass that through. Good, I agree. Let's do that. Pass the 2 through, and it'll become -10y plus 2z equals -18. And then the bottom equation, -2y minus 2z equals -6. And then add down again. And when I add down this time, I get, let's see, -12y. The z's go away, and I get over here -24. And I can, now that I have that equation, I can just solve that for y, can't I? Just divide both sides by -12, and I get y is 2. Now that came from me messing around with the second and the third equation, right? That's how I got this over here. This y equals 2 came from basically messing with these two and then adding them together. So I am now allowed to replace either one of these with this answer. So I'm going to go one last final kind of step here. I'm going to rewrite this as x plus y plus z equals 6. And then -5y plus z equals -9. I'm leaving the second equation alone, but I'm replacing the third equation with y equals 2. I'm going to write like this, y equals 2. I don't need the y in the middle, but I just wrote it there just to line it up with the other y's. Okay, so everyone, we know what y is now, right? Okay, if we know y, look at the second equation. If I know what y is, then can't you find out what z is? right? If I know y is 2, I can come into this equation, replace that equation, that y with 2, and then I can solve this for z. So then I'll know what z is. And if I know y and z, right, then I can go to the first equation, replace y with 2 and z with whatever we're going to get here in a minute, and then you can solve for x. So we're at the end now. We're going to do the back substitution step of elimination, which is to just start plugging things in. So we know y is 2. And then if I take equation 2 now, which is the second line here, and write it, negative 5y plus z is negative 9, and replace the y with 2, then we get negative 10 plus z is negative 9, and add 10 to both sides, and you should get z is 1. So now I know what z is. And then I'll do it over here so you can see the equation. Equation 1, I'm going to go back to equation 1 up here. And that's x plus y plus z is plus z equals 6. That means x plus, now y we said was 2, and z we said was 1. If that equals 6, then that means x plus 3 is 6, which means x is 3. So x is 3, y is 2, and z is 1. So the way we write this answer, the way we normally write this answer is we write it as an ordered, what we call an ordered triple. An ordered triple, which means we want to write x comma y comma z, which for us would be 3 comma 2 comma 1. That would be our answer. So the way it works is that, you know, back last class, we were getting answers and they would refer to a point on a flat sheet of paper where our two lines hit each other. Here, we're saying that these three planes, these three flat sheets of paper, are hitting each other at a single point. And that point has an x coordinate of 3, a y coordinate of 2, and a z coordinate of 1. So I don't know how many of you have had some experience graphing in three-dimensional space, but that would be that's what an ordered triple is. It's like an ordered pair, but you need a third coordinate there, and that's your z coordinate right there. So what do y'all think? Any questions?
At the beginning of the problem.
The beginning of the problem.
Added the first and the third equation.
Wait a minute, hold on. Let me move this. I gotta find it. Hold on, it's up right here. Let me move this up here. Okay, at the very beginning of the problem, what now?
If we had added the first and third equation,
Mm-hmm.
we would have gotten x straight away, right?
Exactly. So going back and looking at this back again now, right? If we had another opportunity to think through this, there's a thing on our notes that says that you can interchange any two equations in the system, right? You don't have to leave anything in the same position. What's being pointed out here is look at the first and the third. If you were to just have started off with the first and third, let me get this, I'll copy it. If you did the first and third to start, it would have got real nice, real fast, right? So if I take those two equations and the third one and add those down, right? You don't even have to do anything, just add them down. You would get 2x, the y's and the z's would cancel and you get equals 6, which means x is equal to 3, right? Okay, now what would you do next? That would be kind of my question. What do you want to do with this? You would do it, so you would just replace the x in the first and third, is that what you said?
And the second.
And the second, so you would just replace all of the x's with 3s.
Yeah.
Okay, and then you just move that number to the other side and solve? That would be fine. That'd be fine. That would be a fast way of doing it. Not every problem's going to work like this, but when you're doing them, I would look for maybe things like this because it can cut down on your time. It doesn't illustrate the method. Let me see what our next example looks like here. Hold on. Like something like this one, right? Where there's not something super clean like that, where you can make the X and Y go away, or X and Z go away at the same time. This is more likely what you're going to run into. So to address your questions, yeah, I mean, if you see that, go for it. It'll probably speed things up, but just don't expect that to always be the case. All right, any other questions on this? All right, so would y'all like to get, let you try and work this yourselves, or do you want me to just work through it? What do y'all think at home? What do y'all want to do? Me work it, you work it, and then we go over it together.
I kind of think I need one more.
You need
If
one
you
more?
don't mind.
Yeah, I don't mind. I don't mind. All right, so I'm going to work with this. I'm going to take, are y'all okay with that? Is everyone all right with that? Amanda spoke up, so.
Sorry, guys.
No, it's all right. It's good. If you want to do it
Yeah,
yourself,
I need another one.
you can just mute me. All right, here we go. I'm going to just start with the first and second equations, okay? And I'm going to try and make the x's go away. All right, so I'm going to do this on the side. I'm going to take a little system over here. I'm going to do x plus y minus z equals -1. Hey, and so, you know, I didn't mention this, but I will now. I mean, there's so many places where you can make little mistakes, right? With your signs, or, you know, it's like if you mess one thing up, everything's going to fall apart. So just be careful. Just be careful. Writing down the first two, right? Even if you like write one of these wrong, it's over at that point. Okay, so there we go. There's my first equation. There's my second equation. I want to make the first equation go away. So Amanda, since you wanted to see this, what should I multiply the first equation by, Amanda, to make the x's go away?
Can we just do 4?
4. Okay, so if I do 4, then I'll have a 4 here, and it'll be 4 plus 4x, 4x plus 4x. That won't go away.
Mm-mm.
You're close. You just don't want them to be the same sign, right?
Yes. So 2.
Nope. 4 is right, but you need it to be negative, don't you?
Oh, -4. Yes.
Yeah,
I'm
there you go.
sorry.
Okay, so -4 here. Then when you put it through, you'll get your x's to cancel.
Yes. Hold on.
-4x, -4y, +4z equals 4. So multiplying everything by -4, be careful. Now your bottom equation, we're not changing. Now I can add these straight down. So let me add now. When I add them down, I get -7y plus 6z equals 20. So I took the first equation, the second equation. I multiplied the first equation by -4. Then I added the two together and I got this answer. What should I do with this answer? What do y'all want me to do? There's two things I can do. Somebody tell me what they want me to do. There's two choices.
Can you plug into the middle?
Middle. Let's replace the second equation with that answer. Everything else will stay the same. Okay, so x plus y minus z equals -1. And then I'm now going to replace the second equation with this answer we just got. And then the third equation, well, I haven't touched it. I'm about to, though. So I'm done. That was kind of like my first little step over there. Now I take the first and the third equation and try and make the x's go away here also. So here's my first equation, x plus y minus z equals -1. Then 2x minus 2y minus 3z equals 5. What do you say?
-2.
-2. -2. Let's do that through. So we get -2x minus 2y plus 2z equals 2. And then the other equation stays the same, 2x minus 2y minus 3z equals 5. And then I add these down. And when I add down, I should get -4y, the x's are gone, minus z equals 7. And what do I do with that? Two choices, right? Replace the first one or the third one with it. And it really doesn't matter. I'm going to replace the third one because the third one's more complicated looking anyway. And this is kind of the normal procedure, is to leave the first one alone the whole time and just always work with this, the second and third ones. It's tedious. -4y minus z equals 7. All right. So the whole idea was to work with the system to eliminate the x's. Now we have two equations with two unknowns on this, the second and third equations. I should be able to solve those using the stuff from last class. Are y'all watching me for errors, making sure I'm not making any mistakes? Let's do this. I'm going to go to a new page. All right, so now working with the second and third over here on the side, I have -7y plus 6z equals 20. And then the other one is -4y minus z equals 7. All right, what would you all do here? And who's got an idea of how we can eliminate? Do we have to do the y's or z's? Are we free? Do we get to choose? What's the deal here? Yeah, we can get rid of the z's, but it's your choice at this point, right? You can do the y's or the z's. It's up to you. Now, just keep in mind, when we were doing what we did, the two steps before this, we eliminated the x's and we wanted to get the x's out of there. Now that we get to this, what you get rid of is completely up to you. You can get rid of the z's or the y's. I think the z's are the easiest, right? Because you would multiply the second equation by 6, right? Second equation by 6. I think that's the easiest way to go, right? I agree, and that's the way I would normally do it. I'm going to just do something different because I want you all to see you could, right? That you can do this. Watch. I'm going to multiply the top equation by 4 and the bottom equation by -7. I'm going to do that simultaneously. And the reason I'm doing that is I'm going to turn, I'm going to try and kill the y's off. So the -7, -4, those don't look like they want to go away unless I multiply the top by +4, which gives me -28y. If I multiply the bottom by -7, I get +28y. I'm just doing that just to show you it can be done. And this definitely is not what I would do, you know, if I had free will to do whatever I wanted here. I wouldn't do this because I'm actually presenting myself with more room for error here, but it should all work. So let me see, I get -28y. Let's not screw this up. Okay, and now 4 times 6, so plus 24 z equals 20 times 4, which is 80. And then on the other one, that should be a positive 28y, and then a positive 7z, and then a negative 49. Then this add down goes away there on the y's, the z's, 31z. And then over here, I hope this is divisible by 31. I mean, it is 31, great. And then that means if I divide both sides by 31, I get z is 1. And I'm going to take that answer and I can replace either the second or third equation with that. So I'm going to go ahead and replace the third one. And we're pretty much at the step now where you do the back substitution. The numbers have been nice here, haven't they? Like we've been having really nice integers as answers. I want to point something out. This is the reason I actually solved for z here. There was something I wanted to point out to you that will come up next class or not, next week. Notice that if I rewrote this, there's a 0 here, a 0 here, and a 0 here. It's like you've got no x's and then a y, z, and a number. Here you have no x's, no y's, and then z and a number. What we've created here is this thing that's like a diagonal. Y'all see that diagonal there? We've got zeros below the diagonal. This is actually something that when we talk next week about matrices, this is what's called echelon form, row reduced echelon form when you get this diagonal. I just want to point it out right now. It'll come up again next week. Don't worry too much about it right now. The great thing about having zeros there, though, if you have a 0 here, 0 here, 0 here, if that's the case, then you definitely know what z is. If you know what z is, you can come back and get y. And then if you know z and y, then you can always come back and get the first equation. So getting that diagonal like that is kind of the goal. So next step, I take equation 2, which is negative 7y plus 6z equals 20. And I replace the z with 1. Subtract 6 on both sides. Divide both sides by negative 7. I get y is negative 2. And then I can go to equation 1, which is x plus y minus z equals negative 1. And I will replace the y with negative 2. I'll replace the z with 1. Careful there with your signs, equals negative 1. So this becomes x minus 2 minus 1 equals negative 1. So x minus 3 is negative 1. Add 3 to both sides, you should get x is 2. So as an ordered triple, right? As an ordered triple, the answer is 2, negative 2, 1. Questions? Let's not lose sight of what we've just done. Here was the original problem, right? What was our answer? 2, negative 2, 1. Okay. What we're saying is that if you plug in 2 for x, negative 2 for y, and 1 for z, the first equation will be true. And the second equation will be true. And the third equation will be true. That's what we have found. All 3 equations simultaneously are true when you replace x, y, and z with those 3 numbers respectively. All right. the next thing I want to do is I think I want to see if you can figure this out now. I want to give you time to think about this. Can you figure out a parabola that goes through those 3 points? So we know that all parabolas look like y equals ax squared plus bx plus c, right? All parabolas must look like this. And I'm asking you to figure out what a is, what b is, and what c is, all right, for the parabola that goes through these 3 points. And that's all I want to say. I want to see if you can figure this out without me giving you any other information. At least can you get the system of equations set up? All right, and I'm going to let you do that. I'll check back with you in just a minute. I'm going to just take a quick break. Do you guys get your system set up already? Okay. How about you all at home? Were you understanding what you're supposed to do? Think about what these points represent. If I tell you the point -1, -4 lives on this parabola, that means when you plug this in for x, this is what should come out for y. Which means that if I take my general formula for the parabola, if I replace the x with -1, the y should turn into -4, means this y should become -4. If I replace the x, not the a, the x with -1. So when I plug -1 in for x, this parabola better spit out -4, which means that -4 must be equal to -1 squared times a, that's 1 times a, that's just a, and then -1 times b, which gives me minus b, and then plus c. So that first point, the first point gives me my first equation. Right there, I have 3 unknowns, but I only have 1 equation. The other 2 points are going to give me the other 2 equations, and all of them together will give me 3 equations, 3 unknowns. Does that make sense at home? I know. Say again, Carissa?
I was just going to say yes, sir. It does make sense.
Okay, good. The next point being 1, 6 means that when I take my general equation, which I don't know what it is, if I replace x with 1, the y should be 6. So I should have 6 over here. Replacing x with 1 in this is actually kind of easy because it's just going to be a times 1 plus b times 1 plus c. So there's my second equation. And then my third equation is from the point 3, 0, which means when I plug in this time 3 for y, I mean 3 for x, I should get 0 for y. So this should become 0 equals, let's see, if I replace x with 3, I'm going to square it. 3 squared is 9. A, and then if I replace x with 3 here, I should get plus 3b plus c. And there's my third equation. I now have 3 equations and 3 unknowns. So I'm going to set up a system of equations. It should be, let's see, the first equation, I'm just going to write as a minus b plus c equals -4. The second equation is a plus b plus c equals 6. And the third equation is 9a plus 3b plus c equals 0. Now, this system of equations, I have different variables, right? It's not x, y, z. It's a, b, c. But you should still be able to follow the same procedure to figure out what the values of a, b, and c are. Y'all good at home? Understand? Any questions? All right, let's solve this. I'm going to try and go a little faster than I have in the previous ones. I'm going to start with my first 2 equations. Oops, I'm not going to do that. I'm going to start with my first 2 equations. I'm going to write those down over here real quick. A minus b. Let's see if I can do this without making a mistake, because that's the biggest issue is you try and go too fast and you mess up. Okay, I'm going to get rid of the a's. Okay, I'm going to get rid of the a's. This is where you could go after the b, but I'm going to get rid of the a. So I'm going to multiply top row by -1 top equation. So I get a new equation here. Negative A plus B minus C equals 4. And then the bottom equation didn't change. Add straight down. I get nothing. I get 2B. Oh, the C's canceled. Equals 10. I got B is 10, B is 5. I already know what I already know what the second. I already know what the second variable must be. Must be 5. So I get to replace either one of these with this. So I'm going to replace the second equation with this. B equals 5. Then I still have my third equation. Now, a little tip here. I could continue the process right now. I could go and say, oh, let me do the first and the third and then work through that, right? I could do that. However, I know what B is, right? I know what B is. B is 5. I got it. We got B on that first step. So if you want right now, you can rewrite this system and you can replace all your B's with 5. So your first equation becomes A minus 5 plus C is negative 4. Your second equation is still B equals 5. And your third equation is 9A plus 3 times B, but B is 5, so 15 plus C equals 0. And the good thing about that is on your first equation and your third equation, you can move the 5, this negative 5, move it to the other side by adding 5. And then here, so I'm going to add 5 here, add 5 here. And then here, subtract 15, subtract 15. And what you'll have is a new system, which gives you A plus C equals, we added 5 to both sides, 1. And on the bottom equation, we could add the 15, we get 9A. And then we still have a plus C equals negative 15. And in the middle, you still had B equals 5. But look, the first and third equations right now, 2 equations, 2 unknowns. So we can just do what we did last time. All right, we can just do what we did last class on those. Okay, so I'm going to take the first and third, A plus C equals 1, and 9A plus C equals negative 15. And I'm going to get rid of the A's. I could get rid of the C's also. Do y'all care? You want to do A's or C's? I don't care. C's, you want to get rid of C? Okay, negative 1, boom, boom, boom. So we've got negative A minus C equals negative 1. The bottom equation is still 9A plus C equals negative 15. And then add down. The C's cancel, you get 8A equals negative 16, and divide both sides by 8, and you get negative 2 for A. So now we know what A is, now we know what B is, right? We already knew what B was. So to get C, I'm going to go to equation 1. A plus C equals 1. I'm going to replace A with negative 2, because we just found what A was. And then add 2 to both sides, and you get C is 3. So I think I've got it. It's as a triple, it's negative 2. What was B? B was 5, right? 5, and then 3. That's your A, that's your B, that's your C. Now I have not answered the question. The question was to find the parabola. So remember, the parabola had to look like this. And we just figured out that A has to be negative 2, B has to be 5, and C has to be 3. This parabola is the unique parabola that should go through the 3 points that they gave us. So to answer the question I asked at the beginning of class, you need 2 points to define a line. You need 3 points to define a parabola. And this is the way you can do it for any parabola. You can do this. Give me 3 points, and I will guarantee get you the parabola that goes through them. Now I'm going to verify this answer with a graph. I'm going to go to Desmos, and I'm going to have it graph y equals, what was it? What was A? Negative 2x squared plus 5x, what was C? Plus 3. Okay, so there's the parabola. Now, what were the points that we were given? -1, -4? Okay, so you all see it there? It just showed up. There it is. That lives on the parabola. Okay, what was the other point? Or there were 2 more, so 1, 6 and 3, 0. There they are. Do you all see them? There's the -1, -4 that lives on the parabola. Here's the 1, 6 that lives on the parabola, and 3, 0 lives on the parabola. That's kind of cool, huh? That's kind of an interesting idea that you just need 3 points to define a parabola. What do you think? Do you think for a third-degree polynomial that you might need 4 points? Like this is a quadratic, right? This is a parabola, second-degree polynomial, x squared. We needed 3 points. What do you think? If it was something like with x cubed, do you think we need 4 points? Yeah. But your system of equations would be 4 equations, 4 unknowns. And then you just keep going up. You always need 1 more point than the highest power of the polynomial. And that's what computers do. This is called regression modeling, okay? So that's what computers do. I'm not sure how many of you have ever played with like Excel. I'm gonna play a little game here. We're gonna do something here. I'm gonna create some data, some random points, 2, 3, 4, 6. I'm just gonna create like 10 things, and then I'm just gonna create some just random numbers here. -2, 3, 6, -1, 1. Okay, so I've just created some random points. I'm going to have the computer insert a, which one is it? Here we go. Where's my scatter? No, I don't want to do that. And do it this way. Oh, you know what? Okay, so let me make this bigger. These are just some like random data points. Can you all see those okay? Does the screen look blurry to y'all, or is it just my eyes? Is it blurry over here? Yeah. It looks blurry, doesn't it? I think we need to refocus that thing. For those of you at home, y'all don't have this problem right now.
I can see it okay.
Yeah, at home, I think y'all are fine. It's here on campus. Which one is it? Marker options. There we go. There. Okay, there we go. All right, so here's some random data points. Actually, let's do 2 data points, okay? If I go to my data and I right-click it and I add Trendline, what's going to happen is the computer is going to try and fit something to this data. And right now it's doing a linear, what's called regression. So it's trying to fit a line between these two, which it's 2 points, so it could do it, right? Easily. And I can even have it display the equation of that line right here for me. This is the equation of that line. Okay. Now, if I do 3 data points, now it's trying to fit a line to 3 data points, but it can't, the three points don't have to all be in line. So it does something where it fits what we call the best fit line. It's trying hard to fit a line, but it can't. But I can change it. I can change that data, the trend line. Okay, I can change it from linear to a polynomial. Quadratics are polynomials. So I'm going to change it to a polynomial of degree 2. That's quadratic, right? And I can ask it to display the equation on the chart. And do y'all see that I know it's hard here. You see, it just fit a perfect, see how the parabola goes through all 3? That's because 3 points define a parabola. Now, what if I instead go to 4 points? Well, that parabola is no longer going to fit, but it'll be a pretty good, it's trying, right? It's trying to do it. Well, I should be able to do it with the 3rd degree polynomial. So let me try it again with 3rd degree. I'm sorry, I should be able to do it, yeah, with 3rd degree, because it's how many points now? 4. Okay, so let's try this. Let's do a polynomial degree 3. Look at that. I need to get rid of those other trend lines. I'm afraid. There we go. Look at that. See? 4 points uniquely define a 3rd degree polynomial. Now, what you eventually want is to be able to do as many points as you want. Now it's trying to fit a 3rd degree polynomial to 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 data points. If I have 10 data points, then what am I going to need? A 9th degree polynomial is what it would take to go through all these points. Let's see, can it handle a 9th degree? I don't think it can. I don't think the software here can. Let me see how high it'll let me take it. Degree 2. Watch how it gets better. Let me get rid of this one. Or let me get rid of both. Okay, here we go. I'm going to add a trend line. Polynomial. So it's trying a quadratic, not very good. 3rd degree, not that great. 4th degree, 5th, 6th, 7th, 6th. That's as high as I can go. That's it. Now this is Excel. There's other math programs that you could go way higher and it will fit it to it. All right. We're limited, but that's what's going on here. That's basically what's going on in the background is what we were doing, that solving of a system to try and find something. Pretty cool. Another kind of aspect of this is I'm not a huge, I like sports, but I'm not a big baseball fan, but I do know this about baseball. If somebody hits a home run, right? Here's someone's playing baseball. Here's their bat. That's awesome. And they hit the ball, right? And here's the stands, and here's all these people in the stands. They're all, yeah, cheering or whatever. And the guy hits the ball and it goes up, whatever, parabola, and it hits into the stands, right? They'll tell you that that home run would have gone a certain distance had the fans not been there. They will actually tell you, you know what, let me change something here, make it a little easier. So here's the stands, okay, and here are all the people. Hits the ball, hits the stands, and they will tell you, oh, look, that home run, how far did that ball go? The distance from here to here doesn't really tell you how far that ball would have gone, right? What would make more sense is to try and measure what would have happened if you allowed it to come down and hit the ground, right? Right there. Then you measure that distance. but it hit the stand. So how are you ever going to know how far it would have gone? Well, we have a way using modern day technology. We know where it left the bat, right? We basically know one point where it left the bat, right? We can figure out where it hit in the stands. And so all we need is one more point. So they can measure one other point on the path of the ball. As long as they can measure one other point, that's all they need. Then they can come up with the parabola, right? Then they have the equation, right? Bx plus c. They have it. And if you have the equation, then how can you find this point? If I give you the equation of a parabola, of this parabola, what does this point really represent? The x-intercept, right? How do you find the x-intercept? You take this equation and set it equal to 0, right? So you can actually predict how far something would have gone without it actually having to go there, because you have the quadratic model. Once you get that model, find the x-intercept, you got it. Make sense? So it's kind of cool. Kind of cool how that can be done. But you have to solve a system of equations at some point. And we use computers to solve systems because computers are very fast. All right. How are we doing here? Good. All right, let's look at another example. So I wanted to show you an example of an inconsistent system. Inconsistent, meaning that something is going to go wrong here. Remember when we started this, we said there's these different possibilities, right? You have, okay, what we've been doing, that's consistent, right? You have one solution. We have not seen an inconsistent system yet. So that's what this example is. All right, so let's go after it. I'm going to take the first two equations. I'm going to set up a little system here on the side with those. And I'm going to try and make the x's go away. So x plus 2y minus z equals -9. I'm going to multiply, what do you say, second equation by -2. That sound good to you? Okay, we've got 2x plus y minus z equals -2. And then -2x minus 4y plus 2z equals 18. Add straight down. -3y plus z equals 16. So far, everything looks okay, right? Nothing is weird. Everything seems to be in place. I'm going to take the system, rewrite it. I'm going to replace the second equation with the answer I just got. So -3y plus z equals 16. And the third equation, just leave it alone. All right, now I'm ready to start working with the first and third. So when I do the first and third over here, I hope you're okay with me. Well, oh no, I won't go that fast. Okay, 2x plus y plus z equals -2. And then x minus 4y plus z equals 1. Hey, same thing. I'm multiplying the second equation by -2 again. Just happens to work out that way. So I get 2x plus y plus z equals -2. Minus what? What? Did I write it down wrong? Is minus what? Oh, I wrote it down wrong from the, oh, the original up here. Wait a minute, I wrote it down wrong right in here, right? Okay, sorry, everyone. See? Right there should be a minus. That's this right here. So that only changes this right here. This is going to be a minus right there and a minus right there. Fix those. Thank you all for paying attention. Okay, that so far that shouldn't change anything, right? We should still be good. Negative 2x here, plus 8y. We're multiplying, not adding. Okay, and then we have minus 2z equals negative 2. Add straight down. 0, let's see, 9y minus 3z equals negative 4. Yeah? That will become my third equation, that answer. Move this down. So I'm rewriting this, but I'm replacing the third equation with that answer. 9y minus 3z equals negative 4. My first equation I'm not changing, except for that minus sign there that I messed up. All right, now let's work with the second and third equations, right? Let's go work with those. And this is where we're going to have a problem, all right? So let's go take a look at what happens to those. I do the system negative 3y plus z equals 16, and then 9y minus 3z equals negative 4. Let's get rid of the y's by multiplying the top equation by 3, right? Because that'll make the 9y cancel with negative 9y. And we distribute through, we get negative 9y plus 3z equals 348. Yep. So multiply that through, we should get this. And add down now. And what happens when we add down? All the variables on the left go away, which means you have nothing on the left. On the right, you have 44. And so you're saying 0 equals 44, but that's not true. And that right there tells you that this is inconsistent. And that was the same thing that happened last class. If you ever got like a number equals some other number and it's not true, then you know it's inconsistent. That would be where the two lines were parallel in last class. Now what we're saying is that one of these three things is happening. Either they're all parallel to one another, or this is happening. Just out of curiosity, I don't know, all of y'all have different backgrounds when it comes to this stuff. Does anybody here know? Where's the problem? There it is. Does anyone here know how to be able to look at an equation of a plane and tell whether or not they're parallel with one another? The z variable, how do you mean? No. There's an easy way. This is just a preview for you. If you go on later on and do more math, there's a really easy way to tell whether or not planes are parallel to one another. The way you do it is you look at the coefficients of the variables. So the coefficients of this one are, the first equation are 2, 1, and negative 1, right? See that? 2, 1, negative 1. Now you have to do these in order. The next one is 1, 2, negative 1, okay? And then the last one is 1, negative 4, 1. The way you can tell if they're parallel is if if you can multiply this by some number and get this. Or multiply this by some number and get this. So for example, to be parallel to this, if I had something that was like 4, 2, -2, that would tell me I'm parallel to this. Because to get from 2, 1, -1 over here, all you have to do is multiply by 2. This turns out to be called what's called the normal vector of the plane. But that's something you actually cover in calculus 3, is when you start talking about normal vectors of planes. But in physics, it might come up also. When you start talking about vectors and then planes and then normal vectors. So there is a way to easily check that these are parallel. So I can tell you right now, just from what I already know about this stuff, is that it's not this. Because these are not multiples of one another. Those numbers up there were not multiples. There's no way to turn 2 into 1. Well, I'd have to multiply it by a half. But then if I do half of 1, I don't get 2. So these are not scalar multiples. So they're not. So it's that other case where they're hitting each other, just not all at one point. All right, so back here, so I say right here, inconsistent, right? No solution. Now we have the other case, right? Where there is an infinite number of solutions. Was it 220? Yeah, so let's work through this one. This is I think this is the most confusing one. All right, here we go. All right, so I'm going to take the first and the second. I'm going to try and get rid of x. So I'm going to do this a little faster. I'm trying to get rid of x, so I'm going to multiply the top equation by -2. I'm doing this right off the bat. -2 times the top one. -2. -2 equals -16. So right there, I took equation 1 and I multiplied it by -2. Right, that's how I got that top one. And then the bottom one is 2x minus 3y plus z equals 23. Add down. You should get y plus 3z equals 7. That's going to be my second equation, right? I'm going to go a little faster now. Watch. I'm going to do the first and the third now. I'm going to just do those over here, the first and the third. And what do I need to multiply by in order to make the first and third cancel for the x? -4 across the top. Let's do that. So -4 on the top plus 8y plus 4z equals -32. So I just multiplied the first equation by -4, so it would cancel with the bottom equation. And now I add down 3y plus 9z equals 21. And so I'm kind of like doing these steps really fast so I can come back and rewrite the original system now, replacing, I'm going to leave the first equation alone. I'm going to replace the second equation by what we did the first time over here. So y plus 3z equals 7, and replace the third equation with what we got that second time we did this, which is this. And now I'm going to work on the last two together, these two. So I need to do that over here. Let me see if I can squeeze that in here. Let me move this down a little bit. Is everyone following what I'm doing? Any questions? I know I'm worked a little faster through this over here. Let me get this system going. I have y plus 3z equals 7. And then the other one is 3y plus 9z equals 21. Let's get the y's to cancel. So multiply the top one by -3. Do that there. So we've got -3y minus 9z equals -21. And then the bottom equation didn't change. And now add down and, oh, whoa, what happens here? Left side, everything goes away, right? And the right side, everything goes away. You get 0 equals what? 0. That's true, right? That's true. So what in the world are we going to do here? What in the world are we going to do? 0 equals 0. So that means I can replace one of these equations with what? 0 equals 0, which means I really only have these two equations, right? These are basically, these are, what does this mean? What is the relationship between these two lines? That's right, just the blue parts, right? That means they're the same line, right? It's the same line. So I'm not going to gain any information. Basically, what this is telling me right now is that my new system looks like this. X minus 2y minus z equals 8. And then the second equation I have is this. That's it. That's all I know. Because that second equation and third equation are the same equation. I know that because I got 0 equals 0. So there's an infinite number of answers, right? Do you all agree there's an infinite number of answers? Now, there is something else I can do, all right? I can tell you what all the answers have to look like. All right, so I'm going to say right now at this point, infinite solutions. But I'm going to go further. I'm going to try and tell you what the ordered triple looks like. Okay, I want to tell you what it looks like. All right, so watch what I do here. This is tricky. I'm going to take this equation here and I'm going to take the second equation and solve it for y. Y equals 7 minus 3z. Okay, I took this equation, solve for y, because it's easy to solve for y. And then I'm going to take that and I'm going to stick it right in here to the first equation. I'm going to replace the y with what we just said it was, 7 minus 3z. Minus z equals 8. So I took the first equation, x minus 2y, but I replaced y with this. I'm going to distribute the -2 through. I'm going to get my x's. Well, let me just clean it up is what I should say. I'm going to get my z's together here. 6z, take away 5z. I mean, take away z is 5z. And then I'm going to move the 14 to the other side, which should give me 22 when I add 14 on both sides. And then I'm going to solve for x. I know that's weird, but let me try and explain what's going on here. I have an infinite number of solutions, but they can't just be any numbers. They actually have to live on the planes. So here's what I can tell you. I can tell you that the y coordinate is 7 minus 3z. So let's write that down. In the y coordinate down here, the y coordinate is 7 minus 3z, right? And what's the x coordinate? Well, the x coordinate has to be 22 minus 5z, right? So that has to be 22 minus 5z. And the z coordinate, well, the z coordinate can be anything. So it's like if you tell me what z is, I can tell you what the y is, and I can tell you what the x is. This represents the infinite number of solutions. For example, if z is 0, what's the ordered triple? If z is 0. So plug 0 in for z here. What do you get? 22, 7, 0. That point is a solution to the system. Let's do another one. Z is 1. If Z is 1, you get 22 take away 5, right? Which is 17. And then 7 take away 3 is 4. And then Z was 1. Do you see you can like build up all the solutions this way? Yeah, that's the strangest case that you're going to run into in your homework. And you'll know it's happening when you get one of these over here to be 0 equals 0. See how it goes with this, okay? See how this goes. I think that we have enough here. I've given you kind of an example of each case. We did the parabola of curve fitting. Yeah. So this is your homework. See how it goes. Some of these may have one answer. Some of these may have, you know, no solution. Some of them may have infinite. But we'll call it a day because I don't want to start doing the word problems. But that's what we'll do on Wednesday. Again, if you can't be here, I understand. I would appreciate if you just sent me a text or an email, or probably an email just saying, hey, I'm not going to be there Wednesday. Just so that I'm aware. And then I'll record everything and post it on YouTube. And yeah, everybody, I will either see you Wednesday or I'll see you next week. Okay.
Bye. Thank you, Professor.
Okay.
Bye.
If anyone has any questions, I'll hang out for a minute. If not, see you later.